So first we need to figure out, with this video, we're going to go over a little bit about what we see in our equations. So these symbols are what we would see in an equation. And these units are what we need to know in order to discern what kind of thing we're given in word problems. For most of physics, we keep it very straightforward. F is for force, A is for acceleration, M is for mass, V is for velocity. There are a few things as we get further in physics that won't follow that pattern, but it's partly because we've already used one of the letters associated with that. So for example, momentum. We can't use M for momentum because we already used it for mass. So later on, we'll see a different symbol for momentum in our equations. But force is a push or a pull. Its unit is newtons, capital N. So anytime we see like 5 capital N, we know that's 5 newtons. A newton is a combined unit, so it's got kilograms times meters divided by seconds squared, kind of wrapped all into one. But because it comes up so often in physics, physicists decided that it needed its own special unit so that we could just, rather than writing kilograms times meters divide by seconds squared every single time. M is for mass. It's the amount of stuff in an object, and by stuff, the more scientific, more precise way to say that would be matter. But it's the amount of electrons and neutrons and protons and quarks and molecules that is in an object. The symbol for that is M, and the unit for that is kilograms. And in physics, we use kilograms instead of grams because of how large our objects usually are. So for example, in chemistry, most of the time you use grams because the quantities of the items are so small. So a gram is about 1 grain of rice, or a small lady's stud earring, or if you're at the school I'm currently teaching at, we have these purple restroom slips. One of those purple restroom slips is about a gram. A kilogram is about the size of a textbook. It's about 2 pounds. It's significantly heftier, and that's because in physics, we're dealing with heftier things. We're not dealing with drops of liquid or little piles of powdered chemical. We're dealing with planets and rockets and like cars crashing into each other. They're significantly heftier. Acceleration is the change in an object's velocity over time. So anything over time is a rate. So if that word comes up, it's the we could say acceleration is the rate of change of a velocity. And this also comes up in pre-cal. So if you get to pre-cal and they ask you to find the rate, they're asking you to find something divided by time. Most of the time in our equations, acceleration is an A, but we do have one special one, G. G is still an acceleration. G is not a force. This G is not a force. This is the acceleration caused by the force of gravity. So this G is still an acceleration, and on the planet Earth, it's roughly 9.81 meters per second squared. Sometimes I write that as A with a little g next to it to help students realize that the acceleration caused by gravity is an acceleration. It's not its own thing, and it's not a force. One thing I forgot to mention up here is that anytime you see one of these symbols with a subscript next to it, the subscript is just describing what force it is. So I wrote Ft, F little n, F little g. Those things are describing, the little letters are subscripts that describe the big letter. So in this case, force, capital F, all of those things are forces, all of those things are pushes or pulls. It's just describing what's causing the push or the pull. So force of tension, normal force, force of gravity, force applied. Those are all things, force of friction. Those are all forces, and the little letter is describing the force. We could even have the same thing for masses. If we're in a situation where two masses combine or collide or crash into each other, we might want to know the mass of one of the objects and the mass of the other object. And the way we're going to distinguish that is with some sort of like 1 or 2 for the first object and the second object. Our new one here is the coefficient of friction. If you're in my regular on-level class, you don't need to worry about the coefficient of friction. This is more for honors physics, K physics, AP physics 1 and above. But it's a measure of how sticky a surface is. And it has a Greek letter as its symbol, and the name of the Greek letter is mu. And it doesn't have a unit. Another thing to keep in mind is that in physics, we use words very specifically and very precisely. In physics, for example, we've already seen that velocity and speed are similar to each other, they're related to each other, but they're not quite the same. But at least with velocity and speed, if we're given a velocity, we can often, or if we're given a speed, we can often plug it in for a velocity. And this is also okay because they have the same unit. So speed and velocity are both measured the same way. However, weight and mass are two completely different things in physics. It's not even the difference between speed and velocity, where they're a little different, but mostly the same. In physics, weight and mass are a little bit the same, but mostly different. Don't confuse weight and mass in physics. Weight is going to be a force. And it's specifically the force of gravity pulling on an object. So when you see Fg for force of gravity, also think of that as the object's weight. In some physics classes, weight will be denoted with a W. I prefer force of gravity because they are so very similar, and I just stick with Fg. Mass is the measure of stuff. You're not going to change the mass just by moving it to a different location, even if it's a different location in the solar system. And we also have to be careful in our word problems. In word problems, we can be very sneaky as physics teachers, and we can say a 5 Newton box. And we can say a 5 kilogram box. And we expect you to understand that that unit is telling us something very specific about the properties of that box. In this case, this is the weight of the box, and in this case, it's the mass of the box. And we'll see how that can make a difference in one of the questions we have about a rocket. Another thing to keep in mind is that forces are vectors, which means the direction matters. So when we write down all of our summation equations, it doesn't necessarily matter what order we add them in, but it does matter whether we have the forces going up or going down, left or right, which would also be negative or positive. It also matters whether we have multiple forces. So say this is our free body diagram. In this situation, it might be we've pushed an object, it's got friction to slow it down. So we would have pushed this object to the left, and now friction is making it slow down. Got gravity, and we've got a normal force. When we write our summation equations, we would have to be careful about which forces we need in which summation equation. So vertical forces would be in one summation equation, and horizontal forces would be in a separate summation equation. If you're in my on-level physics, you don't need to worry about angles and sine, cosine, and tangent. But you do still need to make sure that things that are going up are positive, things that are going down are negative. Right is positive, left is negative. So let's start with an example. In this example, the reason I have this example is to show that for our summation equations, it isn't always just something, one force minus another force. There can be more than one force, and it can look different depending on the situation. So let's see how this problem goes. My recommendations for solving force problems is first to draw the free body diagram. So in this case, free body diagrams start out as a box, and then we put the forces that are pushing or pulling on our object. In this case, it's the man and the scaffold that we're worried about. And the reason it's both the man and the scaffold combined is because it's asking us to find the tension in each cable. So we need we need all the objects that are affecting the tension in the cable to be our part of our free body diagram. And that's the scaffold, which is attached to the cables, but it's also the man inside the scaffold. So even though the cables are not attached to the man affects how much tension is in the ropes. You've felt this before if you've ever had to carry a full box versus an empty box. You are only touching the box itself, but whether the box is full or empty will affect how much force, how much effort you need to carry the box. So we need to include the man in this. Our forces, just about every time we're going to need the force of gravity. The only time we won't need a force of gravity is if we say an object is in deep, 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 deep space, where the force of gravity from the sun is negligible and the force of gravity from any planet is negligible. Now, how many upwards forces do we have? This situation right now would be an object that's just plummeting. So hopefully for our window washer, that's not the case. Hopefully there's some upward forces to balance this out. And in this case, we should have 4 upwards forces because there's 4 cables. Ft for force of tension. The second step I always have is write the summation equations. So writing down the summation equation just says that we write the net force. So some physics teachers like to write the net force as F net. Personally, as a physics teacher, I don't like that because it can very easily be confused with Fn for the normal force. And I feel like students understand better what F net means when I write it this way. So this is another Greek letter. This is sigma. And what sigma means is add up all of the whatever follows. So for example, if we wrote sigma m for something, that would mean add up all the mass. And just like delta meant change in something, if we have delta x, we have change in position. Delta v means change in velocity. Same thing with sigma. Sigma means add up all of the whatevers, and in this case it's all the forces. So this is another way of writing the net force. And the reason we use the word net is the same way we use the word net for net worth. So if you think of Elon Musk, he has a net worth of so many billion dollars, right? What we're saying when we say he has a net worth of that much is we're saying his cars plus his house plus his Tesla business plus his SpaceX business minus any debts he might have for whatever reason, all of those things added for his possessions and subtracted for his debts, that would be his net worth. So it's the same thing for net force. We're adding up all the forces. The net force is not its own force. So in our summation equation, we have net force equals, and then all of the forces that are caused by actual objects are listed out afterwards. So in this case, we have the 4 cables pulling on the scaffold. So that's 4 forces of tension. And they're all upwards, so they're all positive. And then we also have the force of gravity, which is downwards. So the force of gravity is going to be negative. And because this is not an AP Physics 1 question, we can assume that this guy is sitting smack dab in the middle of the scaffold and all of the tension is the same. And just like if we have x plus x in math, we can get 2x, we would have 4 times the force of tension here. Still keep the force of gravity and bring down this net force on the other side. Our third step is use Newton's second law. And what I mean by use Newton's second law is we're either going to plug in 0 for the net force, or we're going to plug in mass times acceleration. So Newton's second law tells us the relationship between the net force and the object's mass and its acceleration. So we're either going to plug in 0 for the net force, or we're going to plug in mass times acceleration, since mass times acceleration equals the net force. When do we plug in 0? And when would we plug in mass times acceleration? We plug in 0 for the net force when the acceleration is 0. 0 times any mass equals 0 net force. And there's two situations when we have 0 acceleration. One of those situations is when we have no motion. We're at rest, we're staying still, we're not moving. The other situation would be at a constant speed or constant velocity. We plug in mass times acceleration for the net force when we are accelerating. And in physics, accelerating means getting faster. It also means getting slower. And it also means changing directions. So if we're turning, we're accelerating. Okay, so what is this window washer doing? The window washer is staying still, so that means we plug in 0 for the net force. Another thing to keep in mind is that when the net force is 0, we can say that the forces are balanced. So that tells us, well, I'm going to pause there. So kind of the fourth step that we need to take. The first 3 steps, we need to have a general idea of what the situation is, but we don't need to know what we're solving for. That's why I like using these 3 steps so much. You don't need to know what you're solving for to get started. But once we get to the end of step 3, we kind of need to take a step back and ask ourselves, what are we trying to find? In this case, it's the tension in each cable. So this is what we're trying to find. That means we need to know something about the force of gravity. So how do we calculate the force of gravity on an object? The force of gravity is the object's mass times the acceleration caused by gravity on the planet Earth. So what mass are we going to use and what acceleration are we going to use? The bigger question, hopefully the acceleration that we're going to use, is 9.8 meters per second squared, because that's the acceleration of all objects on the planet Earth when they're not affected by air resistance. But what mass? Are we going to use 100 kilograms? 200 kilograms? 300 kilograms because we need both? What do you think? In this situation, we're going to use 300 kilograms because like I said at the beginning of the problem, it's going to matter whether the scaffold is empty or full, just like it would matter to you if you were carrying an empty box or a full box. So there is somebody sitting in the scaffold, so we need a mass of 300, the man's mass plus the mass of the scaffold. And 9.81 is our acceleration caused by gravity. So the force of gravity pulling on the scaffold and the man is 2,943 newtons. So down here in our summation equation, we can plug in 2,943. So now this turns into an algebra problem, and we're just solving for our unknown variable. So we add 2,943 to both sides. So we get 2,943 equals 4 times the force of tension. So we divide by 4 on both sides, and we get 736 newtons. Now, in my class, we don't really go over the scientific notation and significant figures. So for me, if you just want to keep 3 digits, that's okay. So like 152, 25.7, 1.25, right? So keeping 3 numbers as your final answer is good. But when you're doing your calculation, don't round until the very end. So keep as many decimals as you can until the very end. What force is needed to accelerate a 50-kilogram box 7 meters per second squared if friction is 150 newtons? So let's draw this picture. First, free body diagram. We know there's a force of gravity. If there is friction, that means it's on some sort of surface. We're going to assume that the surface is horizontal. So that means if the surface is horizontal, the normal force, the supporting force, so the normal force is the force that a surface provides so that you don't fall through the floor. Is straight up on a horizontal surface. We have some sort of applied force, and we have the force of friction. I like to have the force of friction going negative. That's my preference, but it's not required. You can have this image switch the other way around. Second step, write the summation equation. So if you're at home, try to pause the video and write the summation equation that you think fits for this situation. Okay, so for our summation equation, we won't have all 4 forces in one summation equation. We would have 2 summation equations, one for the y direction, which would be the normal force minus the force of gravity, and we would have one for the x direction, force applied minus the force of friction. Also keep in mind that sometimes the forces, they don't need to be so specific. You could have force push. If you don't want to write force applied, that's fine. Third step, apply Newton's second law, or use Newton's second law. In our y direction, are we accelerating? What would accelerating look like for an object in the y direction? It would look like either the object was falling or it was being launched off of the ground. And that's not happening for our y direction. So we have 0 equals the normal force minus the force of gravity. In the x direction, are we accelerating? Yes. It specifically tells us that we're trying to accelerate this box. So we have, in this case, rather than plugging in 0, we use mass times acceleration. All right, so we've gone through our first 3 steps, and now we need to take a step back and actually ask ourselves, what are we trying to find? In this question, we are trying to find the force needed to accelerate. And that's a little bit ambiguous, but what it's asking us to find is this applied force. So what force is needed is saying, what force would we need to provide to this box in order to make it accelerate with this amount of friction? So we're looking for the applied force. So pause the video and see if you can go from there. The mass of the object is 500 kilograms. The acceleration that we have is 7. And like I said, this one doesn't really, it doesn't say with an acceleration of ... It kind of just slips the 7, our acceleration in, and we need to recognize, yes, that's an acceleration from the units that they gave us. Force applied is what we're trying to find, so we leave it alone. And the force of friction is 150 newtons, which was provided in the question. 500 times 7 is 3,500. And then we add 150 to both sides. So our applied force equals 3,650 newtons. Now, one thing I want to point out with this one is it's really deceptively simple. Like, we have just a few numbers, it's not really complicated, and it could be really easy for students to think, oh, I got this, I can do it in my head, right? But as a physics teacher and as somebody who also took high school physics, I know that it can get really confusing real quick for, do I need to add this force or do I need to subtract this force? Am I going to multiply mass times acceleration and then add? Am I going to multiply mass times acceleration and subtract? Am I going to divide? That can get really confusing if you don't write things down. And the reason I say to have these 3 steps, free body diagram, summation equations, mass times acceleration, those 3 steps are to prevent you from getting lost in your own head when you're trying to do the problem. So I'm not trying to suggest these steps as a way to slow you down. I'm suggesting them as a way to help you prevent making easily preventable mistakes. A 30-kilogram object is moving on a frictionless surface at a constant speed. What force is being applied? We could go through this one with our 3 steps, but I don't want you to. What is the answer to this question? A 30-kilogram object is moving on a frictionless surface at a constant speed. What force is being applied? We have a really important keyword here, right? Constant speed. Constant speed tells us that our acceleration is 0, and it also tells us that our net force is 0. Is there any force that is already acting on our object that would make it slow down or make it slow up or speed up? Not in this situation. We have a frictionless surface. So if we are on a frictionless surface at a constant speed, there is 0 force being applied. This is also Newton's first law, which says objects in motion stay in motion. The only reason we see objects slow down is because there's already that outside force making the object slow down. Let's see if we can go through this one with our 3 steps just to prove it to ourselves. So in this case, we have an object. We know there's a force of gravity, and we know there's normal force because it's on a surface. It says frictionless, so there's no force to make it slow down. But let's just say we're not so sure about the applied force. So let's put in an applied force, even though we don't need one, right? Hopefully you should see from the free body diagram that if we don't need to have any horizontal force, because then our forces would be unbalanced. So anytime there's only one force on an object, we know that it's accelerating. Whether it's the force of gravity pulling something down, or whether it's friction making something get slower, both of those are unbalanced forces which cause acceleration. But let's just put the applied force there just in case. Our summation equation in the x direction would then look like this. And then we need to apply Newton's third law. And since we're moving at a constant speed, we know that our net force is 0. So what does that show us about our applied force? It shows us that there is no applied force. So that's another reason why I say these 3 steps are good. If you're unsure, you want to check something, you can use these 3 steps in any situation. So here's the rocket problem that I was talking about earlier. A very small rocket weighs 20,000 newtons. Its engines exert 25,000 newtons of liftoff force. What is the mass of the rocket, and what is the acceleration when it lifts off? So let's do free body diagram. At a rocket, we know the rocket has the force of gravity pulling it down, and we know that the engines will provide a certain amount of thrust. So in our summation equation, we have the force of thrust minus the force of gravity. And now we apply Newton's second law. And it does ask us about the acceleration. So mass times acceleration equals the thrust minus force of gravity. Okay. So now that we've got that, let's go back and ask ourselves, what are we being asked to find? First question is, what is the mass of the rocket? So take a second, think to yourself, what is the mass of the rocket? And do we need to solve for it? It's tempting to say, we don't need the mass of the rocket, it's given to us. But remember, weight is not a mass. And we've got that unit there to kind of show us as well. Mass needs to be in kilograms. This is the force of gravity. So we need to solve for the mass. So we are given 20,000 newtons of force, solving for the mass, and the acceleration due to gravity is 9.81 meters per second squared. So I get the mass is 2,038.7 kilograms. And like I said, if this is your final answer, so as a final answer, you can just write 2,040 kilograms. That would be an appropriate answer. However, we're going to need that mass for calculations, so it's good to go back when we use it for calculations, use the longer number. If you have a graphing calculator that keeps the decimals, or you can grab the number and use it a lot easier, then keep as many decimals as the calculator allows. All right, so the next question says, what is the acceleration when it lifts off? So again, we found the mass, 2,038.7. I'm going back to the larger number now that we're using calculations. The acceleration is what we're trying to find. The thrust was given as 25,000 and the force of gravity was given as 20,000. So we have 5,000 on one side, and then we have to divide by the mass that we found. So 5,000 divided by 2,038.7. And I get an acceleration of 2.45 meters per second. So that's all the examples I have for today. But one last thing before I end the video is I want you to realize, also realize how I write down the problems. So as a physics teacher, sometimes I notice that students will, it's okay to have a separate calculation in the corner, but I'll see equations over here, and then I'll see some numbers plugged in over here, and I'll see maybe an answer, maybe, but it doesn't have a box around it, so I don't know. There is a specific reason why I write my answers the way I do. It's not only for you, it's also for me. Imagine if you were trying to like when you're writing your equations all over the place, it is so easy to just forget something. So make sure that when you're writing down equations and you're plugging down numbers, everything gets brought down step by step, right? Don't just leave off. And another thing is I see, and it's really strange, it's very, very strange to me, people will leave off the equal signs. That I don't know how to solve a problem without an equal sign. So make sure everything gets brought down. I've also seen strange things where like the a disappears, the variable disappears. Make sure every number is plugged in, and if you're trying to solve for it, make sure it gets brought down. Okay, so I hope that was helpful. If you have any questions, you can always reach me during tutoring.